Vibratory motion, wherein we look at periodic motion or simple harmonic motion, spring motion, and pendulum motion. Say you have an object and you attach an object to a spring, you pull the object a distance x, and you let go of the object. Due to the action of the spring, the object will move back and forth. This type of motion is known as vibratory motion. The simplest type of vibratory motion is called periodic motion or simple harmonic motion. Characteristic of simple harmonic motion is you have constant period and constant amplitude. Period is time for one vibration, and amplitude is the maximum distance that the object can reach, maximum distance from equilibrium position. Position wherein the spring is neither stretched nor compressed. Also, characteristic of periodic motion is at equilibrium position, the velocity or the speed is maximum, while at the amplitudes, the speed of the object is zero. Spring motion is just one example of periodic motion. In spring motion, the one responsible for maintaining the vibratory motion is, of course, the force applied by the spring or the spring force. The spring force here is therefore referred to as the restoring force. By definition, the restoring force is the influence or force responsible for maintaining the vibratory motion. As such, the spring force is called the restoring force in spring motion. The inverse of period is called frequency. Frequency gives us the number of vibrations that the object can make per unit time. The unit for frequency is hertz. Periodic motion is described by three functions: the position function, the velocity function, and the acceleration function. The position function describes the position of the object as a function of time. Velocity function gives you the velocity of the object as time passes on. And of course, acceleration function gives you the acceleration of the object as a function of time. Note that in using these three functions, particularly in using the cosine or the sine function in these functions, be sure to set your calculators to radians. Angular frequency, unit of which is radians per second. The angular frequency omega is equal to 2 pi divided by the period of the periodic motion. Hence, it is also equal to 2 pi times the frequency. The phase constant, unit is in radians, defines the position of the object at t is equal to 0. The maximum values for the position function, velocity function, and acceleration function are as follows. X max is equal to the amplitude. V max is equal to the amplitude times the angular frequency. And the maximum acceleration A max is equal to the amplitude times the square of the angular frequency. Now, specific to spring motion, again, specific to spring motion, you have the following equations. The angular frequency is equal to the square root of k over m, where k is the spring constant of the spring. And the total mechanical energy at any position in the motion is always equal to 1/2 Ka squared. Another example of periodic motion is pendulum motion. You have an object tied to a string of length L, and you allow the object to swing back and forth. This motion is reminiscent of vibratory motion. In particular, if we let the angle of the pendulum motion, the swinging angle theta, to be very, very small, the more the motion of the object resembles periodic motion. So for very small angle theta, the following equation applies for the angular frequency. Omega is equal to square root of mgl over I, where I is the moment of inertia of the object. I is equal to ml squared. The period of the vibratory motion is equal to 2 pi times the square root of L over G. So that's it for now. We'll talk about the examples for vibratory motion in the next video.